This is an explanation of how distance vector routing works. Our problem will assume a autonomous system that has 4 networks, A, B, C, and D. The networks use a distance vector routing algorithm to exchange routing information. Assume each router only initially knows about its directly connected neighbors and the cost of those edges. And assume all distance vectors arrive at the same time, and processing works from left to right, A, B, C, D. This last assumption is actually very important for us because otherwise it becomes very tedious to do these problems by hand. But there's also a bit of give back, which we'll see as we sort of solve this problem. That the fact that we have to process 3 requests at the same time means that if the order of those 3 changes, the arrival time of those 3, then our routing table also changes. But I'll explain that as we go along. Okay, so over here we have 4 routing tables. Each router on the autonomous system will maintain its own set of routing tables. Okay, this is a distributed algorithm, and the router initially knows about its directly connected neighbors. Okay, so A knows about itself, of course. To get to itself, it costs nothing. To get to B, it costs 2. To get to C, it costs 9. And to get to D, it costs 5. Okay, this will form its first distance vector. So this over here, we have a distance vector. Okay, distance vector is just the cheapest known cost to get to any particular node. Okay, over here, B is not connected to C, so it has a cost of infinity. And inside of this, I'm going to represent infinity as just a blank cell. Okay, and in the distance vector, I'll actually put infinity. Internally, inside of the router itself, okay, because it doesn't know that C exists at this point, there's no actual column for C inside of the implementation version. The reason I put this column C is because I'm going to be sending this data to neighbors left and right, and it's going to mess up the column ordering if I don't include this sort of blank cell over here. So over here I just put an infinity symbol over here. But normally routers, they just add additional columns as they learn about other devices. Okay, but over here I'm just going to leave it empty, as well as the B column over here empty, just because it otherwise it makes everything much more confusing if I have to match columns. Okay, C has a cost of 9 over here and a cost of 2. D has a cost of 2, 2, and 5. 2, 2, 5, and to get to D it costs 0. Okay, so what's going to happen is each of these devices are going to exchange distance vectors. So A's distance vector goes to B, goes to D, goes to C. C's distance vector goes to A and D, and etc. Okay. And so essentially these yellow boxes over here are exchanged. And so let's change my color to green. So what arrives is from B, it's going to be 2, 0, infinity, 2. So I'm going to write down. So that's going to go over here. So essentially you can think about this as from, and this is 2. Okay. So 2, 0, infinity, 2, 2, 0, infinity. I'm just going to leave blank, and 2. And from C, it's 9, infinity, 0, 2. 9, infinity, I'll leave it blank, 0, 2. From D, I receive 5220. 5220. And let's see, from over here, from A, I receive 0295. From D, I receive 5220. And from C, I don't receive anything, so it's still infinity. Okay. From here, A, I receive 0295. B, I don't receive anything. And D, I receive 5220. From A, I receive 0295. From B, I receive 20 infinity 2. And from C, I receive nothing. Okay. So the next step is to calculate the new distance vector. Okay. So in fact, we are now at t equals 1. Okay. So the new distance vector at this point is going to be the cheapest cost to get to any particular node. Okay, so our original cost was 0. There's no way anything can be cheaper than that. It's going to be 0. And for B, it's 2. Over here, we have a cost of 0, but that's just going through B, and the cost to go to B is 2. So that's still going to be 2. And for D, the cost is 2. The cost to get to D is 5, so that's 7. So you can think about this as, well, B can get to itself in 0, and it costs me 2 to get to B, so that's how I'm getting the first one. And the other one was, well, D can do it in 2, can get me to B in 2, but it costs me 5 to get to D, okay? And so to get directly to B, the original path is cheaper, okay? Next one is C. So this is my original path to C, okay? And D says they can do it in 2. So D says they can do it in 2. But how much does it cost for me to get to D? Well, it costs me 5. Okay, so notice that it does not see this path yet. Okay, that path it does not see. So it only sees this one. And so, but that still is cheaper. 5 plus 2 is 7. So that's going to replace this existing path. Okay. And this is where I mentioned that timing matters. Okay, so over here, original cost to get to D is 5. And over here, we learned that B can get us to D in 2. And it costs us 2 to get to B. Okay, this the same circled one. So this is going to go down to 4. Okay. Now imagine that. So this is just because we're working left to right. But imagine that, and this also assumes that all 3 of these distance vectors arrived at the same time. So I received B's distance vector, C's distance vector, and D's distance vector. But imagine that I received B's distance vector first. Okay, maybe 1 second earlier. Okay, and that makes sense because this connection is faster than D's connection. Okay, so it's very possible that this might happen. So in that case, this would update to 4, and then when I get D's distance vector, it would update this to 6 instead, because it would be 2 plus 4 instead of 2 plus 5. So you can see we give up a little bit by processing 3 at a time, but it simplifies the complexity. Otherwise, it's almost impossible to draw this table. But just note to yourself that in the real world, these distance vectors are computed as they come in. So you don't compute sort of like the entire table at once. You compute one row of this table, calculate you update your routing table, and then another one comes in, and then again you update. Okay, but again, for simplicity, we're just going to do it all at once. That gives us 2, 7, 4 over here. And again, that's not optimal because we know that we can go 6 over here in that path. Okay, so it's better, but it's not optimal. But again, as we continue to iterate, we'll get better and better results. Okay, and so for the next one over here, the original cost is 2. Okay, this one costs 0 plus the cost of 2 is the same. The 0 over here, you can't beat 0. This one's infinity, so anything beats it. Okay, so let's look at the first one. This one says 9. Okay, and the cost to get to A is 2. So that's saying that I can go this way to get to C. Okay, and so that's 11. And maybe I'll put that here. Okay, but immediately it gets erased because, of course, 4 is much cheaper. Well, yeah, 4 is much cheaper. So that would be this 2 plus this 2. Okay, so maybe I had 11 for 1 second. If A came before D, okay, I would have 11 inside of here. So the order in which it receives these distance vectors really does matter. And then the last one doesn't change, 2042. Let's see, I'm gonna shift this a bit because it's otherwise gonna fall off. Let's see, so over here my original cost is 9, which is pretty expensive. There's a cost, okay, so this one we can ignore because that's A, and to get there it's gonna cost me 9. So 5 over here is interesting. Okay, so 5, how much does it cost me to get to D? It cost me 2, so that's going to be 7. Okay, next we have infinity, so anything is better than infinity. So let's see, let's look at this one first. This one is via A, and it's going to cost me 2 via A. It cost me 7 to get there. 7 plus 2 is 9. Okay, so that's from C. I can get to A in 7. Okay, so that's 7. And then from A, it can get to B in 2. So that's how I get to 9. 2 plus 5 plus 2. Okay, and of course that's much worse than going by a D. So that would be 2 and 2. So 4 is going to be the results. But again, it's timing dependent. If I get A's before I get D's, then that value would be the larger 9. Just because anything's better than infinity. Next is 0. And then 2, and this 0 over here requires that I add in the existing 2. So, yep, 7402. Let's see, over here, 5220. So 2 plus the cost to get to B is 2. So that's 4. Okay, so we're doing better. And then these don't look like much. 2, this 2 0, yeah, 9, 2 is way cheaper. And let's see, right, this is 0 because it's myself. Okay, so after t equals 1, these are the distance vectors that we calculate. And then again, these distance vectors that we just calculated go out onto the wire. Okay, they're shared with all the neighbors. Okay. And so this is getting a bit messy, and I have a cleaner version that removes the first distance vector. So this updated version is after all the distance vectors have been exchanged. So you'll see 0274 inside of here, inside of all of them, in fact. 2042, which was sent over to A and D. D sent over 4220 to each of these. So all the distance vectors have been sent, and essentially they just replace the old values that were in them before. Okay. And then using this new routing table, we again calculate the cheapest costs. Okay. So 0274, that's gonna stay 0. 2042. Again, there's nothing to improve over here. This 0 is gonna cost me 2 to get there. So this is gonna stay 2. Over here, let's see. So our original cost is 7. It looks like we can improve over here. The cost to get, if I send it to B, it's gonna cost me 4, and only cost me 2 to send it to B. Okay, so that'll be 6. And if I send it to D, it's gonna cost me 2, and it cost me 4 to send it to D. So both either way is fine. If I send it next, next we have 4. Over here, if I send it to B, it's gonna cost me 2. The cost to send it to B is 2. If I send it to C, if I send it via, or if I send it to C, C can get me 2, but the cost to get to C is 6. So that's gonna stay 4. Let's see, next we have B. And so B's cheapest cost is 2. First one stays 2 because A is the only one smaller, and it's going to cost me 2 to get to A. Next one is 0. Over here we have 4. We have 2 over here, but it costs me 2 to get to D, so it stays 4. And then over here we have 2. And again, to get to D, it's going to cost me, 2. So that's why I have a 0 over here. Next we have this one. So we have an original cost of 7. And let's see. So going via D will cost me 4. Okay, and to get to D, it's going to cost me 2. So that's going to be 6. Next I have 4 is my original cost. And via A, it's going to cost me 2. But to get to A, it's going to cost me 6. So that's 8 already, way over. And then down here, we have 2, but to get to D, it's going to cost me 2. So that's 4. So it's the same. Okay. Next we have 0, and then 2, and the only way via that is D, which is the same path. Okay, and so over here we have 4220. And so 4, okay, you have 0 over here. But to get to A, it cost me 4, so that one is the original path. We have 2 over here, but to get to B, it's going to cost me 2, which is going to be 4. And then these, nothing really comes close to 0, but then it costs me 2 to get there. This one is 2, and so I'm already anything that I add to that's going to push me over. So this stays the same. Okay. And then at this point we would do t equals 3, but at this point we've reached sort of equilibrium. So in fact, all right, at t equals 3 plus, we've reached equilibrium. Basically, there's no better currently known path to each router. So essentially, they would continuously exchange these same distance vectors over and over again, unless something in the network changed. Okay, and the three things that can sort of happen in the network is a new node gets added. Okay, and maybe there's some cost over here, and then this process would again continuously update. Or we could have a connection sever. Okay, maybe this connection breaks, or the cost changes. Okay, or we just lose nodes entirely, and then all those connections break. So in fact, that might be 4. So new node disconnects, the cost change, either more expensive or cheaper, or we lose an entire vertex entirely. Okay.